Let's take a look at the Dennis Sabourin generator. Dennis has built a generator which operates well in that it runs indefinitely, self-powered, while charging a 2G cell phone battery overnight. The construction is very simple. The heart of the generator is a small motor with a yellow plastic float from a fishing net glued to it to make a lightweight rotor which has got 4 magnets attached to the float. The rotor can of course be constructed from lightweight materials if it's difficult to get a float from a professional fishing net. The magnets are N52 grade 20mm diameter neodymium magnets 5mm thick. The motor is powered by a 3.7 lithium-ion battery, and there are 8 output coils positioned around the rotor. The coils are connected in pairs, with the 4 pairs powering the system. Each coil is wound with 2 strands of 0.19mm diameter enameled copper wire, which is standard wire gauge 36 or could be American wire gauge 32. Each strand weighs 50 grams and both strands are wound at the same time. That arrangement allows the coils to be connected as bifilar coils if that is desired. The central core of each coil is made of plastic and is 8mm in diameter with a 6mm diameter hole in the center, and the completed winding is 30mm diameter on a coil which has 33mm of winding space between the ends. When the winding is completed, each coil is given a layer of electrical insulating tape to protect the wires rather than to provide any additional insulation. So the overall arrangement is you've got battery 1 which powers the motor, which spins the rotor. The powerful rotor magnets fastened close by the 8 coils generates an alternating voltage which is rectified by the diode bridge and used to charge the mobile phone battery through a 5-volt USB module. Only 2 of the 8 output coils are shown in the diagram above. The system works well charging battery 2, but the battery number 1 gradually runs down as it is powering the motor, but is not being recharged. To deal with this situation, Dennis uses a switching box which powers a relay for 10 seconds once every 10 minutes. The relay contacts are used to disconnect the charging current from battery 2 and pass it instead to battery 1. The objective is to keep battery 1 charged while the circuit is running. If no switching is used, then battery 1 has to be connected to the charging circuit at all times. But if a fully discharged phone is connected to the system, then battery 1 might have a much higher voltage than battery 2, and so needs to prevent we need to prevent the battery 1 from pouring its current into battery 2. That can be done by using a diode which allows charging current to flow into battery 1 but no current flowing from battery 1 to battery 2. So in other words, the output from the spinning rotor is allowed to flow into battery 1 if needed, but it cannot flow back from battery 1 into battery 2. With this arrangement, battery 2 gets most of the charging current, especially since battery 1 always has a good level of charge on it, and there is a small voltage drop across the diode, so most of the charging current will flow into battery 2. If you wish to limit the battery 1 charging current further, then a resistor R can be placed in the line like this. The resistor there means that the amount of current that can flow through to battery 1 via the diode is kept down by the actual resistance getting in the way of the current flow. The value of resistor R has to be found by experimentation with your own physical implementation of the circuit, but I would expect the value to be low, perhaps 47 ohms or so. If the light is not required, then all 8 output coils can be used for charging. The coils are connected in pairs, and Dennis has an unusual method of connecting them. He has them connected this way. The red and blue is one pair of coils, and there are 4 identical pairs. But the way that they're connected is unusual. You have the current flowing into the start of coil 1, but instead of being connected to coil 2, it's connected to coil 1 of the second pair, which is then connected to coil 2 of the first coil, which then connects to the end of the second coil. That is a most unusual way of connecting the coils together, but it has been found to be particularly good in this circuitry. These are not the bifilar connections you'd normally expect, but the wiring arrangement is very effective. A variation on this, which I would personally prefer due to its increased flexibility and the possibility of creating increased output voltage through different connection methods, is you connect the pairs as before, but you use a separate diode bridge on each of the pairs of coils, each of them feeding a capacitor, and the combined output has all the capacitors connected in parallel. That gives each coil its own rectification and smoothing capacitor, and as each pair acts therefore as a small everlasting battery, there is an alternative to that, and that's to use a voltage doubler circuit for the rectification to nearly double the output voltage when powering a load. And that is done by the way that the diodes are connected. There are only 2 diodes per coil pair, in other words a total of only 8 diodes, but they're organized with 2 capacitors to charge the positive cycle of the AC signal charges one, and the negative cycle of the AC signal charges the other capacitor. The capacitors are individually connected together, and the output then is between the pairs, and that gives you roughly twice the voltage as opposed to the method that Dennis uses. The batteries used in the prototype are lithium-ion types, which have a voltage of 3.7 volts and a capacity of 1200 milliamperes. These batteries have worked very well, but lithium-ion batteries are not the easiest batteries to work with, and they have a strong tendency to catch fire if mistreated, and they're rather expensive, as can be seen here, because you can buy 2 of them, but it's going to cost you £6, which is a lot for just 2 batteries. An alternative which does work quite well is using nickel manganese batteries, which are the same size but only 1.2 volts each. So we would use 3 nickel manganese batteries instead of 1 lithium ion battery. However, the nickel manganese batteries can have a much greater capacity of 2850 milliamperes, and they are fully stable, although when fully charged they should not be overcharged at more than 10% of the milliampere rating of the battery, because the battery life will be reduced if that is done. However, some of these small nickel manganese batteries do not live up to the maker's claims, and so you need to run a load test on any particular make of battery which you may consider using. I recommend these batteries due to their exceptional performance when I tested them. These are Digimax AA 2850 milliamp hour batteries. Consequently, I would suggest replacing one 3.7 lithium ion battery with three Digimax 2850 batteries, and for that you would use a connecting box like this. This box takes three of those standard nickel manganese batteries and connects them together to give you the 3.6 volts of the three batteries connected by the box itself. That will charge up to about 4 volts and will be a good substitute for lithium ion batteries. One of those is required to drive the USB board, which is used to charge a mobile phone. The connector clips then are used with the battery box. They're very cheap and very straightforward. You have the clip that attaches to the box itself, and then bare wire cable at the end, which allows you to solder the ends to wherever they need to go. Where they need to go for this application is onto the board of this 5 volt DC to DC step up boost converter, which is used for charging the mobile phone. The input to this DC-DC converter board is supposed to be in the range of 0.9 volts to 5 volts. So the 4 volts of the nickel manganese battery pack should be very suitable. Suitable magnets are available via eBay. Typically they're like this. There are 5 of them being offered here for just £2.59. The magnets themselves are very powerful. They're 20mm diameter, 5mm thick, cylindrical magnets. These ones happen to be N52 grade, which would be very suitable for this application. The coils can be wound easily by hand, as enamel copper wire is supplied in 50-gram reels, and that makes it easy to wind one coil from 2 of those reels placed side by side on a fixed bar. We can make up coil spools quite easily if we use a power drill and a hole saw set like this one here. These saw sets normally have a saw which has an inner diameter of 35mm. A small sheet of 3mm thick medium density fiberboard MDF can easily be drilled using the hole saw, and each drilling produces one perfectly round disc with an exactly centered hole in the middle. 2 of those can be glued at exact right angles to the center of shaft onto a tube to form a spool of the size wanted. If it's available, plastic sheet could be used instead of the MDF. Plastic tube of 8mm diameter and an inner diameter of 6mm or 1/4 inch is often available on eBay, but failing that, it's actually quite easy to drill a 6mm hole through a short length, say a 30mm length of the 8mm diameter dowel rod. The piece of dowel is held in a vise because it is easy to see for drilling a reasonable hole down the length of dowel, and it's really not that difficult to do. The spool can be clamped to a standard 6mm diameter threaded rod using 2 washers and 2 nuts or wing nuts if you prefer. Then the threaded rods can be clamped at one end with a simple crank handle formed out of a small piece of timber, a clamping screw to grip the rod, and a 20mm length of drill dowel on a screw to form the rotating winding handle. So this is a method for making a very simple, extremely cheap winding device. A simple drilled hole in the vertical sides work perfectly well as a bearing, but keep the length A, which is the distance between the piece of threaded rod going through the coil and the pivot that you hold with your fingers as you spin it, but you keep that dimension A short, means that you don't need much wrist movement, and it's quite easy to turn the handle 4 times a second. A plank around 600 millimeters long makes a good base for the winder. The winding handle part is at the near end, and two 50-gram spools of wire are placed side by side on a rod or dowel at the far end. The longer the plank, the easier it is to draw wire from the supplying spools, as the angle between those spools and the spool being wound is smaller. The supplying spools are each just mounted on a dowel pushed through holes in the side pieces. Be sure to make those dowels horizontal so that the spools don't keep moving to one side or the other as they slide downhill as they're rotated. To start winding a coil, drill a very small hole in the left hand flange just outside the washer. Thread the 2 wires through the hole and wind each a few times round the bared end of a short length of plastic covered wire, and then join each wire to the copper winding wire by soldering it. This only takes a moment, and if you've never soldered, it's very easy to learn and easy to do. Next, use a piece of duct tape to attach the thin wires firmly against the outer face of the flange of the coil spool, and wrap the spare plastic covered wires around the threaded rod a few times so that they won't catch on anything when they're being whirled around. Trim the duct tape so that it's all on the outside of the flange, and so will not get in the way of the wire which has been wound onto the coil spool. The coil is wound by gathering the 2 strands of wire in your left hand and turning the crank handle with your right hand. If you wish, you can clamp the winder to a table or workbench which you are using. The preferred way of winding is to turn the crank handle so that the wire entering the coil spool feeds onto the underside of the spool. That method of winding is called counterclockwise. If you want a clockwise wound coil, you just turn the handle in the opposite direction so that the wire enters the spool at the top. Counterclockwise is considered to be the better way to wind these coils. When starting to wind, guide the wires close to the drilled flange. This is to keep the starting wire taut, flat, and out of the way of the following turns. As winding continues, the wires are directed very slowly to the right until the spool shaft is fully covered. Then the wires are directed very slowly to the left for the next layer, and that is continued right, left, until the coil is completed. Then the 2 wires are duct taped to the plank so that they're kept controlled while you're busy with other things. Then the wires are cut, a few turns taken around the stripped end of a short length of thicker wire, and soldered to make an electrical and mechanical join between the thick wire and the thin wire. The body of the coil is now wound with electrical tape so that none of the wire is visible, and then the duct tape is removed from the spool and the 2 starting solder joints are epoxied to the flange. There's no need to mark the wires at the start of the wires, as the end of the wires come through the drilled hole and the ends of the wires stick out from under the electrical tape, and a meter will tell you which start and which finish are the same wire. In other words, you've got a wire wound coil in front of you with 4 pieces of wire coming out of it. You take one piece at one end and you check both the other ends. One will be open circuit and one will be closed circuit, and that identifies for you which are the ends of one strand of wire. It's not at all difficult to wind these coils, but it will take a few days. For people living in the UK, the best supplier is the Scientific Wire Company, who manufactures the wire. In June 2017 they sold 50-gram reels of standard wire gauge 36, and they sold those for £3.10, including tax. And that particular wire is solderable enamel, which just burns away when you solder to it, which is enormously helpful, especially with very thin wire. An alternative supplier is the frame cable company, which also offers 50-gram reels of 36 gauge standard gauge wire. The big advantage of these small reels is that you can just wind the entire contents of two reels of the wire to make the needed bifilar coil without having to count the turns, and that is very convenient indeed. The motor is a 5-volt fan with the fan blades glued to the yellow float and positioned very carefully to get it exactly centered over the shaft of the fan. The maximum current draw for the motor is 360 milliamps, but as Dennis is running it on 3.7 volts or less, the actual current draw is very small indeed. The underside of the fan looks like this. It shows you the type of brushless fan which he's been using. It's available on eBay, that particular fan, and this is the actual ad for the fan on eBay. It sells for £7.34, or it did when this was first taken, and Dennis invites you to build the generator circuit yourself. Dennis is not expert in electronics by any remote stretch of imagination. He is also allergic to winding coils, so I actually wound the coils for him for this particular circuit.